Hello friends, today we shall discuss solution of questions in transportation engineering which were asked in afternoon session of GATE 2019. The first question is on flexible payment and it is based on recall. It says structural failures considered in the mechanistic method of bituminous pavement design are, and there are four options. Now let me just tell you what is the criteria for failure of a flexible pavement. Now, if this is the layered system, you have the bottommost layer as subgrade, and then you have subbase, base, binder course, that is bituminous binder course, and the wearing course. The criteria of failure which is suggested in IRC 37 is fatigue and rutting. When a load is applied here at the top surface, there is a strain, tensile strain developed at the bottom of the bituminous layer, and that creates the fatigue cracking in the pavement. This strain should not exceed the permissible or allowable limit of the tensile strain. And second criteria is compressive strength, vertical compressive strain at the level of subgrade. And that is the rutting criteria, that this strain should not be more than allowable strain in the subgrade. So answer is fatigue and rutting. That is option number 1. Second question is speed density relationship in a mid-block section of a highway follows green shield model. If the free flow speed is Vf and the jam density is Kj, the maximum flow observed on this section is, and there are four options again. Now, if you know green shield equation, then the maximum flow in case of green shield theory is Vf into Kj by 4. Free flow speed multiplied by jam density divided by 4. If you know it, you can recall this equation. If you do not know what is the maximum flow as per green shield equation, then you can go by basic philosophy. Green shield equation is that velocity of traffic flow at any density k is given by a linear equation, that is Vf into 1 minus k upon kj. Vf is the free flow speed, k is the density, and Kj is the jam density. Q is equal to K into V. That is fundamental relationship between flow, density and speed. So if you take Q as K into V, then this will be K minus K square upon Kj. Differentiate it with respect to K. So you get 1 minus 2k upon kj. For maximum flow, this should be 0. So put it equal to 0, then you get k is equal to half of kj. That is, maximum flow will occur when density is half of the jam density as per green shield equation. And if you put this k in this equation, then you get V is equal to Vf into 1 minus k is now kj by 2. So half, that is half of free flow speed. And maximum flow will be given by this equation. So this will be Vf, half of Vf into half of Kj, that is 1 by 4 Vf into Kj. That is how this equation comes. Third question is, a vehicle is moving on a road of grade plus 4% at a speed of 20 meters per second. Consider the coefficient of rolling friction as 0.46 and acceleration due to gravity as 10 meters per second square. On applying brakes to reach a speed of 10 meters per second, the required braking distance will be. Here let us start with the fundamental, that force required to decelerate a vehicle at, let us say, rate of deceleration d is given by this equation, F is equal to m into d. D is the rate of deceleration. And if F is the rolling friction, then rolling resistance of a moving vehicle is given by this equation. M into G into F. F is the rolling friction. So this is the rolling resistance of a moving vehicle. This is the force required to decelerate a vehicle, and therefore these two must be equal, and that gives you that D into M is M into G into F, or D is equal to F into G. So F is given 0.46 and G is 10, so that is 4.6 meter per second square. That is the rate of deceleration on a level ground. If there is a gradient also, then in that case there will be additional backward deceleration, and this will be equal to G sine theta. This is theta angle. G sine theta is equal to tan theta, because theta is small and tan theta is equal to gradient. So this will be additional rate of deceleration, that is G into tan theta, and tan theta is given as plus 4%. So 10 into 0.04, that is 0.4 meter per second square. So total deceleration now will be 5.0 meter per second square. Now you can find out how much distance is required to reach a speed of, that is simple equation of motion. You can put the values of V is 20 meter per second, U is 10 meter per second divided by 2 into 5, and that gives you 30 meter. This is the answer. Question number 4, and this is of 2 mark. A flexible pavement has the following class of loads during a particular hour of the day. 80 buses with 2 axles, each axle load of 40 kilonewton, 160 trucks with 2 axles, front and rear axles of 40 kilonewton and 80 kilonewton respectively. The equivalent standard axle load repetition for these vehicles will be, as per IS 37, what would be the ESAL, equivalent single axle load. Now 80 buses, 40 kilonewton at the front axle, 40 kilonewton at the rear axle. If you convert them into equivalent standard axle is 80 kilonewton, and you apply here vehicle damage factor. Vehicle damage factor is 4th power law, that is 40 upon 80 whole power 4, and similarly this one 40 upon 80 power 4. This is 0.0625. 0.0625. So front axle is equivalent to 0.0625 ESAL. Similarly this one. So 80 buses will be 80 into 0.625, that is the front axles, plus same with the rear axle, so multiply by 2. This is 10. And similarly 160 trucks, where the front axle is 40 kilonewton and rear axle is 80 kilonewton. Now 40 kilonewton, again it will have equivalent single axle load of 0.0625. 80 kilonewton, because ESL is also 80 kilonewton, so it will be equal to 1. So 160 axles in the front will be equal to 160 into 0.0625, and this will be 160. 160, that is 10. So now total number of axles, standard axles, will be 10 for buses, 10 the front axle of the truck, and 160 rear axle of the truck, that is 180. That is the answer. Next question is also of 2 marks. The uniform arrival and uniform service rates observed on an approach road to a signalized intersection are 20 and 50 vehicles per minute. For this signal, the red time is 30 seconds. The effective green time is 30 seconds. The cycle length is 60 seconds. Assuming that initially there are no vehicles in the queue, the average delay per vehicle using the approach route during a cycle length will be, round off to 2 decimal places. Now, this is based on signal design. What is the average delay at a signal control intersection? And again, if you know the equation, then average delay is given by this equation. dA is 0.5 R square upon C into 1 minus Q upon S. R is the red time. Red time is given 30 seconds. C is the cycle length, that is 60 seconds. Q is the rate of arrival. Rate of arrival is 20 vehicles per minute. And S is the rate of departure. That is 50 vehicles per minute. You can directly put these values in this equation. You can calculate what is the average delay. But this equation is for under-saturated condition, and therefore you must ensure that the condition given in the question is under saturation. Means if there are, how many vehicles are arriving in a cycle and how many vehicles are able to depart in a cycle. Q into C. Q is the rate of arrival multiplied by the cycle length. These are the number of vehicles arriving in a cycle. And S is the rate of departure multiplied by green time. That is the number of vehicles that can depart in a green time. Now, Q into C. Q is 20 vehicles per minute. So, you can say 20 by 60 per second multiplied by cycle length is 60 and S is 50 upon 60 per second multiplied by green time, that is 30 seconds. This value should be less than this value. How many vehicles are arriving and how many vehicles are departing? That basically tells you that is 20 and this is 25. So QC is less than S into G. That is your under-saturated condition. Means each vehicle which is coming in a cycle will be able to depart in the first green. That is the meaning of that. So if you know this equation, put all these values and the answer will be 12.5 seconds. If you do not remember this equation, then go again by the fundamental. At a signal control intersection, this is the rate of arrival Q, which is constant. This is constant throughout the time. The rate of departure is a step function like this, that during green time you have the maximum flow and during red time there is no flow. During green time you have maximum flow and that is the S. That is called the saturation flow. If you plot these two curves Q and S on a cumulative scale, it will be like this. This is the rate of arrival and that is the rate of departure. Now this is the red time when there is no departure and this is the green time. This is the green time. Out of this total green, because we have seen that Q into C is less than S into G, and therefore there will be certain time in the green during which there will be only coming and going of the vehicle. Arrival and departure. A vehicle arrives and leaves. That is that time. Now, the total delay to the vehicles is area of this triangle. This is input, this is output. And area between these input output is the delay to the vehicles. Basically, that let us say this is A, this is B, and this is C. So you need, and let us say this point is D. So you need to know this ordinate CD. How much is this ordinate? And how much is AD? AB. AB is that time. So if you know AB, you know the ordinate, you can find the area of this triangle. Now what is BD? BD is what we call the saturated green. This is the time during which there will be a queue of the vehicle to depart from the stop line. And this will be how many vehicles can depart in a green time. That is S into G. Now this G is not the total G. It is the time during which there is a queue of vehicles. So let us call it GS, saturated green. This will be equal to that all vehicles which are coming during red time, they should be able to depart, plus all vehicles which are coming during this time GS. They should also join the queue. So they will also be able to depart during this time. Now this equation will give you the value of GS. So GS is QR upon S minus Q. Q is 20, R is 30 red time divided by S 50 minus Q 20. So this is 20 second. Now this is BD. This is 20 second. This is 30 second. Okay. So what is CD? CD will be number of vehicles which are departing in 20 seconds. So CD, that is the height, will be S into GS. Rate of discharge is given as 50 by 60 multiplied by 20. So this is 50 upon 3. That is the CD. Now we can find out what is the area. Area of triangle ABC is half of red time 30 into this CD. CD is 50 upon 3. So this is 250. So this area is 250. That is the total delay to all vehicles which are coming in a cycle. And if you want to find out how much is the average delay, you divide this by total number of vehicles which are arriving in a cycle, that is Q into C. So D average will now be 250 upon 20 arrival rate divided by 60 multiplied by cycle length is 60. That is 12.5 second. That is how you can do it. Either you do it directly from the formula if you remember. If you do not remember, just take 1 minute to derive this equation and get the value. Question number 6. A broad gauge railway line passes through a horizontal curve, section radius 875 meter, of length 200 meter. The allowable speed on this portion is 100 km per hour. For calculating the cant, consider the gauge as center to center distance between the rail heads equal to 1750 millimeter. The maximum permissible cant with respect to center distance between the rail heads is. Now here, it's a simple question. The gauge is given 1750. This is dynamic gauge. Millimeter. Speed 100 km per hour. And radius of the curve is 875 meter. 875 meter. What is the equilibrium cant? E. E is G into V square upon 127 into R. 1750 into V 100 100 square upon 127 into 875. This is 157.48 millimeter. Rounded off to the one decimal place. So 157.5 millimeter. Now this is what we call the equilibrium cant. Equilibrium cant is that when the speed is 100 km per hour and the cant provided is 157.5 millimeter, there will be no unbalanced force. The centrifugal force will be completely balanced by centripetal force. Since in the question it is asked what is the maximum permissible cant, so that is the maximum permissible cant, the answer. And the last question is that the speed density relationship of a highway is given by u is equal to 100 minus 0.5 k, where u is the speed, k density, the maximum flow in vehicles per hour rounded off the nearest integer is. Now here, similar to what we discussed in question number 2, u is equal to 100 minus 0.5 k. Because there is a linear correlation between speed and density, so it is a green shield model. In that case, you can find out what is the jam density and what is the free flow speed, and use the equation that the Q maximum is half of the free flow speed multiplied by half of jam density, as I told you in question number 2. Alternatively, you can say that Q is K into U, or 100 K minus 0.5 K square. Differentiate it with respect to K. So this is 100 minus 0.5 into 2K. Put it equal to 0. So you get K is 100. 100 vehicles per kilometer. Maximum flow will occur when density is 100. And when density is 100, what is the speed? Speed will be, that is optimum speed will be 100 minus 0.5 into 100, that is 50 kilometer per hour. So Q maximum will be 100 multiplied by 50, that is 5000 vehicles per hour. That is the answer. So these are 7 questions which were asked in 2019 afternoon session of GATE exam. If you have any questions, you can write in the comment box. Thank you very much.